Embeddings in AI, they are like black boxes. Current XAI methods like Lime only explain one prediction at a time. For example, as we know, Husky and Wolf case, Lime revealed that the snow background drove the misclassification. This finds the cause of the error, but not why Husky and Wolf are considered similar or different in embedding space. Distance explainer fills this gap. It explains why two items are close or far apart in embeddings. To measure the distance between two items in embedding space, the authors designed the following procedure. First, the reference item is encoded once, then random masks are applied to the explained item, and each masked version is compared to the reference using cosine distance. Next, all distances are ranked, and the top 10% closest and 10% farthest cases are selected to represent similarity and dissimilarity. Finally, the method aggregates these by subtracting the mean of the dissimilar group from the mean of the similar group. The result is a signed attribution map. Red regions indicate similarity evidence, and blue region indicates dissimilarity evidence. And the magnitude shows the strengths of each contribution. The authors also note that the outcome depends on parameters such as the number of masks, coverage, and resolution. This study evaluated the method using three main metrics. First, faithfulness using low deletion and high deletion curves. The authors show that removing high importance regions changes the embedding distance a lot, while removing low importance regions barely matters. This means the attribution maps really reflect the model's decision process. Second, sensitivity and robustness. Average sensitivity was very low, about 0.16 for B versus fly, for example. So the explanations stay stable even with small noise or perturbations. Finally, randomization. When the model's weights were shuffled from top to bottom or bottom to top, the attribution maps collapse quickly. This shows they depend on the trained weights, not random chance. Overall, the results show the method provides explanations that are both faithful and reliable. Here we focus on the high deletion fraction case. When high importance regions are deleted, the model's ability to distinguish B from fly drops sharply, as you see. This shows that those highlighted regions are truly critical for the model's decision. This slide shows the randomization test as model weights are shuffled, either top down or bottom up. The attribution maps collapse quickly. This confirms that the explanations depends on the trained model parameters, not random artifacts. This is a result of the qualitative evaluation. On the left, for image versus image comparisons, like V versus fly, the explainer highlights wings as similarity and stripes on body as dissimilarity. On the right, for image versus text, captions play a role as references. For example, the caption, "a dog," highlights the dog's body in a dog and car paired image. The key point is that this model works consistently across both image versus image and image versus text tasks. Finally, the contributions and limitations of the distance explainer. Its contributions. It is the first method to explain distances in embedding space, and it works across modalities, extending explainability beyond simple class score. On the limitation side, random masking can sometimes create unrealistic inputs. The method requires parameter tuning, and increasing the number of mask store resolution causes higher computational cost.